So in the previous video, we kind of discussed the domain and the range of functions. In this video, we're going to focus exclusively on how to find a domain of a function. So once again, for those of you who missed the previous video, that's also a hint for you to watch it. A domain is a set of all possible x values of a function. So when we introduced graphs, right, of functions, let me insert just one graph of a specific function. Let's say this one is going to be a polynomial that goes like this. The domain of this function is all possible x values that this function can assume. And I already mentioned that all linear functions and all polynomials have a domain that's all real numbers. So majority of the time, the domain of a function is going to be, it's going to be from negative infinity to positive infinity. And using parentheses, infinities, positive, negative, and numbers is called interval notation. And in this video, we're going to use it a lot to kind of describe the domain of a function in a mathematical way. But some functions that are polynomials or linear equations are fractions. And those will have some specific rules because as you remember from your previous classes, whenever you have a fraction and the denominator is equal to 0, that number is undefined because you can't divide by 0. But for now, let's just consider a few examples where your domain is going to be all real numbers. So example number 1 would be a linear function. That's 2x plus 7. So here, the domain is from negative infinity to positive infinity. Second example would be a quadratic function where we have 3x squared minus 7x plus 5. And here, once again, the domain is, well, all real numbers from negative infinity to positive infinity. In a third case, let's consider a polynomial of a third degree where we have f of x equal to 9x to the third minus 2x squared plus 3x minus 1. Even though it's to a third degree, this polynomial does not include any fractions. So still, the domain is from negative infinity to positive infinity. So what I want you to remember that if you have a function that's linear, quadratic, or a different kind of a polynomial, the domain is always going to be all real numbers. Now things change when we start introducing fractions. Okay, so I'm actually going to put it in red because that's very important when it comes to finding the domain. So fractions are different. And let's consider f of x equal to 5x plus 7 divided by x minus 2. So whenever you see a fraction in a function and you're looking for a domain, the number on the bottom cannot be equal to 0. So how do we find the domain? Well, we basically set an equation that x minus 2 is equal to 0, and we solve for x. So let's add 2 to both sides, and we find out that x equal to 0 will make this function undefined. So when we draw a number line that represents all possible x values, we are going to label positive 2 and basically say, hey, our function can include all of the numbers less than positive 2 and greater than positive 2, excluding number 2. Now, how do we put it using the interval notation? We're gonna say that the domain is from negative infinity to positive 2, and we're gonna use a parentheses to indicate that positive 2 is not included in the domain of this function. Then we're going to use a union sign indicating that this part is the domain and another part from 2 to positive infinity is also a part of this function. And the same goes for any polynomial. For example, f of x equal to 3x squared minus 5x plus 5 divided by 3 plus x. So once again, the denominator of this fraction cannot be equal to 0 because that will make our function undefined. Therefore, let's follow suit from the previous example and write that 3 plus x is equal to 0, and let's subtract 3 from both sides, and we find out that x that will make this function undefined is negative 3. We're going to do the same thing, draw a number line that represents all the x values and label negative 3 on it. We're gonna do an open circle, which indicates that this function does not have a y value when x is equal to negative 3. And we're going to select all of the numbers greater than negative 3 and also all the numbers less than negative 3. And to use interval notation, we're going to say the same thing. That is from negative infinity to negative 3, parentheses, union, parentheses, from negative 3 to positive infinity. So this function is going to be defined for all of the numbers excluding negative 3. So whatever you plug in, negative 4, 5, negative 27, it's going to have a unique y value. But if you plug in negative 3, it will be undefined. And now, how does it occur, or how does it represent in the graph of the function? There's two scenarios. Well, not exactly. I wanted to have a coordinate system with 2 variables, not 3 variables. Okay, so in the first case, we're going to have a polynomial right? And let's say at negative 3, we're just going to have a hole in our graph. So for a specific x value, in this case negative 3, this function won't have a y value. So we can say that y at negative 3 belongs to an empty set. Another case that you might see in this class or in your pre-calculus class would be that you're going to have a function that stops at -3 and continues at a defined y value. Now, this is only going to happen with piecewise functions. So, for example, piecewise function, we're getting a little distracted here, but let me just exemplify that. It's a function that is defined for two different ranges. So, for example, it will be f of x is equal to, let's say, 2x squared minus 5 for all the x's between -infinity and -3, not included. And then the second set, let's say it will be 3x to the third plus 2x plus 3 for all the x's from 3, which in this case will be included, indicating the closed circle right here, to positive infinity. But you're not going to see examples like that for a little bit in your education until you get to pre-calculus or perhaps college pre-calculus, and you start working with piecewise functions that have two different ranges and two different functions for each range. Now, I want to point out another special case for finding the domain, and it's radicals. Okay, so radicals are a little bit different from fractions, but they also indicate similar thing. So let's consider f of x equal to square root of 2x plus 1. Okay, so everything seems to be perfectly normal. Underneath the radical, we have a monomial or linear equation, but what can't we have underneath the radical? We can't have negative numbers, right? So later on, we're going to work with radicals that look like that. Those are called imaginary numbers. So in this case, we're going to write our function slightly different, or find the domain of the function in a slightly different way. We're not going to say that the thing under the radical has to be equal to 0, but we're going to say that 2x plus 1 has to be greater or equal to 0. We can have a radical of 0. That's perfectly fine, but we can't have any negative numbers underneath the radical. Now you can see why we started working with solving linear equations and solving inequalities first before we started working with functions. Okay, so let's solve this inequality. So we're going to say, well, first, let me not skip a step of subtracting -1 or subtracting 1. And now let's divide it by 2. So we can have x on its own. And now x has to be greater or equal to -1/2. Okay, let's draw a number line and label -1/2. Okay, so x has to be greater, so we're definitely going to move into that direction, right? All of the numbers that are greater. But notice that this sign also indicates that -1/2 can be included. It can be equal to. X can be equal to -1/2. So we are not going to have an open circle. We're going to have a closed circle. And if you want to use the interval notation to describe domain of this function, you're going to say bracket. That indicates a closed circle. So that first number is indeed included in the function. So from -1/2 and then to positive infinity. And infinity always gets a parentheses because it's an undefined number. It's some extremely large number that we can always add +1 to and make it greater. Okay, so that's how you find a domain of the function. Let's do a quick review. So whenever you have a rational function that does not include any fractions, like these three, your domain is going to be all real numbers. So from negative infinity to positive infinity. When you start seeing fractions within your function, then you have to remember that the bottom of the fraction, the denominator, cannot be equal to 0. So you have to solve a linear equation. Then you draw a number line and label all of the numbers that can be below that number and above that number. And the most common way to indicate or to label the domain of a function is interval notation, which is represented like this. If you have a radical, then it's a slightly different case. You are not going to have a linear equation to solve. You are going to have an inequality because we cannot have negative numbers underneath the radical. Those are called imaginary numbers, and we're going to work with them a little bit later, but that will make our function undefined. So we need to solve a simple inequality, and then we can proceed in the same way. Draw a number line and select all of the numbers that are greater than that number, but also including the number that we found for x, because we can have 0 underneath the radical. This sign indicates it, okay? And then once again, you can put it in the interval notation, but do not forget to use the brackets to indicate that the first number can be included in the function. Range is next.